Hello all, let's start section 7.4. 7.4, we are estimating population, standard deviation, and variance using a sample, correct? Hopefully you will remember that this population variance, the symbol for the population variance is sigma square, and also standard deviation. For the population, the symbol is, of course, the square root of variance, which is sigma. Correct? Now, if we don't know, if we want to estimate the population variance, we need, we cannot here use z-score. We cannot use here even t-score. We are dealing with another score which is written like capital X but two sides like this, correct? And we call it chi-square. This will be table A4 in your book, and we use chi-square to can estimate the population variance and the population standard deviation. What is chi-score? The formula for chi-score is equal to the degree of freedom, which is n minus 1, times your sample variance squared divided by population variance squared. That will be the formula. Few notation before I go and use the show you the graph of it. N is your sample size as usual. S square is sample variance. And sigma square is your population variance. Correct? The graph of chi distribution is like this. This point is 0. It starts from 0, goes up, and it's skewed to the right. Correct? This will be your chi-square distribution. It's not symmetric. It's not like normal distribution. It's skewed in one side. Let's write down those things. First thing, not symmetric. It's really important that this is not a symmetric graph like normal distribution. It's not symmetric or not symmetrical. Correct? Number 2, all the values means the values of chi-square. They are positive because you see all of them are on the right side of 0. Correct? Then the values of chi-square, or I will just write values, are non-negative. You don't have a negative chi-square. They are non-negative. Correct? Number 3, important point. As degree of freedom, as degrees of freedom, which I will just write here df, you already know df means degrees of freedom, goes up, distribution become more symmetrical. Does it ever become symmetric, this graph? No. It's actually the actual word in mathematics is we can say as degree of freedom goes up, your graph approaches a symmetrical shape, but never reach there. Never becomes symmetric. Its approaches. The shape is almost kind of symmetrical, but still it's not symmetrical. Correct? Last point that I want to raise here with you. Your graph always gives the value. It's different than t, different than z score, gives critical. This one is a big one for you. Critical values for area to the right. This is really a big statement. Different than z-score, different than t-score. In z-score and t-score, your critical value always gives you the area on the left. And chi-square, it gives you the area on the right. Correct? Now, let's do an example. N is given as 12, 95% confident level. Find critical values. Okay, if n is equal 12, I know the degrees of freedom will be 12 minus 1, which gives me 11. Confidence level is 0.95. It means alpha will be 0.05. Correct? Let's even draw this time this. Let's even draw this. I'll try to draw a good shape, kind of. Here we go, not bad. This point is 0, correct? If my confidence level is 0.95, correct? Then this side will be alpha over 2, which is 0.025. You know how to find alpha over 2. You divide your alpha by 2, correct? And this side is also alpha over 2, which is 0.025. One thing to remember, with the z-score and t-score, if you could find one of the critical values on one side, you used on the other side with negative because it was symmetrical. It's not going to work here. It's not going to work with chi-square. Every time that you are looking for the critical values, you have to find two numbers, one for the right and one for the left, which we call the first one chi-square right. We put an R there, and chi-squared, I'm writing the next, I shouldn't write the next, it's chi-squared left. Correct? Let's go to our table. I'll explain the table for you. Let me again zoom in a little bit to explain. Start with the top. You see, actually, your table is divided to the right. This is chi-square right, and also chi-square left. Correct? And also you have here in the first column degree of freedom. My degree of freedom for this example is 11. And my alpha over 2 is 0.05, this one. Then I'll go down. and I'll go this way, which I'll end up with this number, which is 21.920. Correct? The right side is 21.920. Now, what is the chi-square left? Is this the same number? Should I use 0.25 for the left also? Correct? If your left side is 0.25, to find the right side, the area, because I told you the chi-square is giving you the area to the right, not to the left. If you use again 0.25, it means you don't have any variance. Correct? It means you don't have any standard deviation. Your standard deviation becomes 0. Correct? Then how to find the left? 1 minus 0.025, which gives you an area of 0.975. Correct? An area of what? 0.975. Now, going back to the table, for the left, look for that number. Look for the 0.975, which is here. And if you go down, 3.816 will be your chi-square. You see? That's the only difference. For the left side, it will be what? It will be 3.816. 3.816. This is how you calculate your chi-square, how to find the critical values of chi-squared. Chi-squared to the left, chi-squared to the right. Always chi-squared to the left, you see it's a smaller number. Chi-squared to the right is a bigger number. Why I say this? Because right now I will create a confidence interval for you, correct? And if I create a confidence interval here, I will kind of flip these values. I'll use the right on the left and I use the left on the right, correct? We don't have here margin of error. The only thing that we can do here, we build a confidence interval. And what is the formula? We are looking after variance of the population, then less than, greater than. On the right side, you have n minus 1 s squared. Look at this formula, is very the same as the first one that I start. N minus 1 times s squared over sigma squared. But you are looking for the sigma squared. If you do a little bit of algebra here, you can see if you solve this for sigma squared, you just bring chi squared here and sigma squared here up, correct? Then when you build this confidence interval, here you will have in the denominator chi squared, but for the right you are using left. Why? To get a bigger number, you have to divide by a smaller number, not by a bigger number, correct? And on the left side, you end up with n minus 1 times s squared over what? Chi squared to the right. This is your variance. How we go from variance to standard deviation? We take the square root from all sides, right? If you want to find, this is variance. If you want to estimate variance for the population, and if you want to estimate the standard deviation of the population, just take the square root from both sides. N minus 1 s squared over chi squared left on this side and square root of n minus 1 degree of freedom times s squared over chi squared to the right on this side. That was the only difference. Let's do an example. This is a short lecture to explain this, and we will end chapter 7 here. Example, sample of 10 appliances we get a sample of 10 appliances and the standard deviation of 0.15 volt. Construct a 95% confidence interval for sigma square and sigma. What is this example about? For example, let's think about a charger of the cell phone. The companies are trying to keep the variance, the variation in the charger, kind of minimize them. For example, you are carrying an Apple phone and I'm carrying another model of Apple phone, and I ask, hey, do you have a charger? I forgot my charger at home. Can I charge myself? I said, oh, here you go. Use my charger. And I use your charger and my cell phone, boom, explodes. Why? Because the voltage is not the same. It shouldn't be. I come back to you, what you did. I say, oh, it's working perfectly for me, but I lost my phone, right? What the companies is trying to do, they're trying to minimize the variation and voltage in these chargers. That a charger could be used in different phones, at least from the same model, same company. Correct? This example is about that. Now, what we do here, the first thing, we know the standard deviation for our sample, which is 0.15 volt. Correct? Sample size is given 10. Correct? Then the degrees of freedom will be 10 minus 1, which gives you 9. Correct? Now I'm looking for the chi squared to the right, and also I'll find my chi squared to the left from my table. Going back to the table, let's first erase all these red lines. My degree of freedom was 9. Correct? And alpha is 0.5. It means alpha over 2 will be 0.25. Correct? If you come down this way and if you go this way, your chi squared to the right will be 19.023. 19.023. On the left, again, look for the left because I use the same 95. On the left will be, you're looking for 0.975, correct? And it will be 2.700, correct? .700 or 2.7. Now I have these two. It's really easy to build the confidence interval. First, for sigma square, for variance, it's equal n minus 1 times s squared over chi squared to the left, and this side will be n minus 1 times s squared over chi squared to the right, which my sigma square will be less than, you can calculate 9, degree of freedom was 9, times s squared, it means times 0.15 square, divide by left, which is 19.023, correct? And on the left side, it will be 9 times 0.15 square over 2.7. And if you use your calculator, your variance will be between 0.7075 after I round it off, correct? And on this side will be 0.0106. One more thing that I want to discuss, when you are looking for the standard deviation, please do not take the square root after rounding off. Take the square root of number before rounding off, correct? And if you do that, you will end up with 0.274 on the right, and on the left 0.103. That will be your standard deviation. Correct? This was all about section 7.4. I'll stop the lecture here. See you in chapter